recording right now. Okay, so this thing is gonna end up there in my video, in my YouTube channel. Okay, so remember the very first class. Here you go, basic principles, primary definitions, and laws of physics. Okay, so let's update this guy. Okay, recall the building blocks of physics. Okay, here you go. We covered the meter, time, and mass, and now we are going to have a new quantity that we are going to cover, is the temperature. Okay, we already covered position and force, and we covered the laws, the 4 laws of mechanics, the 3 laws of motion plus the law of gravity. And we also have laws of thermodynamics. We're going to cover some of them, not all of them, but there are a total of 4. Okay, but before we go into the laws of thermodynamics, I have to introduce you to the concept of temperature. Okay, that's a core concept in physics. That is something that is in the very core of physics, one of the basic definitions, is not derived of anything else. Okay, so a new temperature, here you go. Temperature is a new core concept in physics. A basic quantity. It is a basic quantity. It's not dependent on any other quantity. It's not dependent on any other definition. Okay, length, time, mass, and temperature are independent of each other. They cannot be written. They cannot be written in terms of anything else. That's what we mean by basic quantity. And we found that was very long ago that was useful to define this concept of temperature. So I like to think, I like to tell my students think about cavemen, you know? I like to say that, what was the physics of cavemen, you know? Maybe they knew about length and time and mass, and eventually, they came up with this concept of temperature, right? That's and how this thing must have started? They didn't have thermometers long time ago, right? Thermometers was invented later on. So the idea of temperature, it started with the senses. How you sense something. Okay, so think about that. The idea of temperature, it started with the human senses. Yeah, the sense of touch. So it was pretty clear at the beginning that they could warm up water, and they could see a difference between warm water and cold water, right? And they would use just their hands to figure out, to get an estimate of what would become later on temperature. And eventually this idea of temperature evolved more, and we were able to build devices to quantify the concept of temperature. So those are the 4 important concepts, and this is the newly one that we're talking about, temperature. That's chapter 6. Okay. There is something interesting about temperature. Okay, temperature can be measured in different ways. There are several ways that you can measure temperature. There are several in other ways. There are different types of thermometers, okay? Out there. The one that you must be most familiar with, you must be most familiar with is the thermometer that uses the lengths of a column of a given substance to measure temperature. That's one way to measure temperature. There are thermometers out there in which you can put liquid mercury, and depending on the temperature, the column of liquid mercury in a bulb would expand and will become higher. That's one way. Okay? So you can use the lengths of a given, the expansion of a given substance to determine temperature. That's one way. You can also use pressure. Here you go, different ways of measuring temperature. By measuring the lengths, by measuring the lengths of a column of a given substance inside a bulb. That's one way. Another way is by measuring the pressure of a gas. Okay? The pressure of a gas correlates with the temperature. The pressure of a given gas correlates with temperature. That's one way. And there are others. There are electrical properties as well. You can use electrical properties to determine temperature as well. Electrical properties are going to study later on. For now, let's stick to those two that you already know, that we have already covered. Okay? So the main scale of temperature is the Kelvin. Okay? And I'm going to explain that to you. However, you folks are most familiar with the Celsius. No, wait a minute, not the Celsius, the Fahrenheit here in the United States, right? Here in the United States, we use the Fahrenheit scale. To measure temperature. But there is another one that's used in countries like Brazil, Mexico, Europe, okay? In most countries, we use the Celsius scale. They all measure the same temperature, although they have different values in different scales. Okay? So let me make a drawing of a thermometer here for you. Here you go. Here we have a thermometer that you all must be very familiar with. It's like a bulb. Okay. This bulb has a reservoir. At the bottom. and in the book he put it as a red color. Here you go. The reservoir is here at the bottom. It's a little bit smaller than that, right? Here you go. I'm gonna put a red color there. Here you go. And a black color in the surroundings. Here you go. And the temperature is measured in terms of this length of the liquid. The liquid can be mercury, the liquid can, I have already seen ethanol inside the bulb of a thermometer. The higher the liquid, the higher the temperature, okay? And we have, like I said, we have both the Celsius scale and the Fahrenheit scale. Here you go. Those scales, they correlate like the following. Here you go. If I put the Celsius scale here, just like in the book, Celsius, on the right, Celsius scale, and on the left, the Fahrenheit scale. Fahrenheit scale. Oops. What happened here? They look roughly like that. This 0 degrees here, the reference of the Celsius scale. Correspond to a different numerical value in the Fahrenheit. They are the same temperature, they just have a different numerical value. Okay? Zero degrees. We call it 0 degrees Celsius. The next one would be like 1 degree. They put it. Yeah, let's put here 1 degree here. Okay. I'm not doing exactly like the book. Okay. The next one is going to be 2 degrees. One, two, three, right? 2, 3, 4, 5. And so on. 1, 2, 3, 4, 5. And so on. Okay, where we have a 0 degrees Celsius, this temperature is approximately, not approximately, it's exactly 32 degrees Fahrenheit, like that. Okay. What we have right in here, what is 0 degrees Celsius? In the Fahrenheit scale, we measure that as being 32. Go. Okay, and there's more. There's one more important difference between the Fahrenheit and the Celsius scale. 1 degree of difference, 1 degree Celsius of difference in the Celsius scale is approximately 2 degrees Fahrenheit. Not exactly, but approximately. So if you have 0 and 1 here, in reality, you know, at this point right in here, it's not going to be 33 Fahrenheit. It's going to be a little bit less than 34 Fahrenheit. A little bit less. Okay, that's how the Fahrenheit scale is built. This guy that came up with the scale decided to do it this way. Okay. The 0 of the scale is not the same. The 0 is something much colder than that, than 0 degrees C. The 0 of Fahrenheit is much colder than the 0 degrees C. Okay. And 1 degree C of difference corresponds to approximately 2 degrees Fahrenheit. It's in reality 9/5. Okay, the distance from here to here, you know, from here to here is 9/5, which is approximately 2. Okay, so here you go. Let's document there in the notes. There is a relation between the Celsius scale and the Fahrenheit scale. There is a important relations between them. 0 degrees C corresponds to 32 degrees Fahrenheit. Correspond to 32 degrees Fahrenheit. Remember, a difference of 1 degree C, I'm not talking about 1 degree C, but I'm talking about a difference of 1 degree C, corresponds to a difference of almost 2 degrees Fahrenheit. Okay, the actual number is 9/5. 9/5. 1.8. The exact number is 1.8. But as a rule of thumb, you can say that if you have to do calculations by head, you can say that's 2 degrees C. Okay? A difference of almost 2 degrees Fahrenheit. Okay? So the conversion, the formula conversion from degrees centigrade and degrees Fahrenheit we call it either Celsius or centigrade, by the way. In Brazil, when I was growing up, we would call it centigrade. We didn't call Celsius. Celsius or centigrade, okay? Celsius or centigrade. Centigrade because it's 100, from 0 to 100. Is the following. Okay, insert. You know, degrees Fahrenheit is like that. Remember, 9/5 is almost 2. It's not exactly 2. It's 1.8. Okay. Which is equal, here you go, I'm going to put it here, equal to 1.8 degrees Fahrenheit. 9.8, no, wait a minute, 9.5 fifths, sorry, 1.89. Here you go, multiplied by C plus 32. Okay? To convert from degrees Celsius to degrees Fahrenheit is the following. To convert from Fahrenheit to Celsius, to convert from Fahrenheit to Celsius, the equation is the following. Okay, here you go. You gotta invert this equation. You pass the 32 to the other side, becomes minus 32, right? Here you go. And then you solve for C. When you solve for C, you have to multiply that value here by half, almost half, 5/9. Okay. So 32 Fahrenheit corresponds to 0 degrees Celsius. What about 0 degrees Fahrenheit correspond to what? You know, let's do some calculations, simple calculations here. Here you go. Example. You know, example 1. Find how many degrees Celsius corresponding how many degrees Celsius correspond to 0 degrees Fahrenheit. Here you go. Try to do that. I'm gonna give you a chance for like 1 minute or so. Just use the formula. Then we do something. Let me put another example here so you can start working the other as well. You know, example 2. Find how many degrees Fahrenheit correspond to 100 degrees Celsius. The temperature of boiling water. I gotta reset my clock here. While you do that, I'm gonna open my other software there. Here you go. Okay, so here you go. How many degrees Celsius correspond to 0 degrees Fahrenheit? Go. I'm going to write down the equation here, 9/5. Can you remember that, you know? I think it's rather easy, right? You cannot forget, don't forget this one, and this one is easy to remember, right? You can say that's 2 minus 10%. 2 minus 0.2, 1.8. That would be a little bit more difficult to remember, but that would be what corresponds to 0 degrees Celsius, 32 degrees Fahrenheit. Right? Okay. Anybody wants to Okay, Christian has given me an answer. Okay. Anybody else wanna? Okay, Raquel. Anybody else? Christian and Raquel. What about the second example, Raquel? There is, I'm gonna tell you about a little rule of thumb as well. Let's see, we have 2 minutes already. Let's wait another 2 minutes for the second answer. Don't forget to put the degrees there, what degrees you're talking about, right? Is that Fahrenheit or it's C or it's Celsius? $245. Okay, while you're doing that, let me take attendance, okay? So I'll give you a little bit more of time to get Blaze. Are you there, Blaze? Yeah.
Here.
Good, thank you. Kayla. Kayla,
Here.
right? Kayla or Kyla? Kayla, right? Kayla, okay. Courtney.
Here.
Okay, Christian.
Here.
Next, Madeline. Let's see if Madeline is here. I don't see Madeline. Next is Cynthia.
Here.
Good. Raquel.
Here.
Raquel, how do you pronounce your name? There in my country, we pronounce Raquel, you know? How do you pronounce it here?
It's the same,
It's the
Raquel.
same?
Or
Okay. Because we have Rachel, right? We have Rachel here in the States. We don't have Rachel there in Brazil, but we have Raquel, yeah.
yeah, it's Raquel, not Rachel.
Yeah, that's what I was thinking. Brittany.
Here.
Brittany Ewing, right? We have 2 Brittany's here. You, Melissa.
Here.
Okay. And if you have time, see if you can access my YouTube account, my YouTube page, right? And see if you can see the videos in there. Okay, if you have time, just and let me know if there's any problem to access my videos there. Like I said, I'm recording the video of this class today in this software that I bought recently, and I will upload in there in case you want to review the class. Okay, Taylor Givens.
Here.
Next, Evelyn Gomez.
Here.
Brittany Gonzalez.
Here.
Jessica Gonzalez.
Here.
Okay. Don't forget to work on the example, right? To practice. Jacqueline Johnson.
Here.
Rhonda.
Here.
Next is Paloma.
Here.
Allison O'Neill.
Here.
Next is Yareli.
Here.
And Brian Silvestri.
Here.
Okay, and let's see how many we have here. 18. There's just one student who didn't show up, right? Madeline. Okay. Oh, don't do that. Here you go. Good. So now let's do the math. Let's do the math. I want to convert from 0 degrees Fahrenheit to C, right? Fahrenheit is equal to 0. What we gotta do is substitute here and solve the equation for C. The first step is to pass the 32 degrees to the other side and solve for C. What do we get? We get minus 160 over 9. It's approximately 16 degrees, a little bit more than that. Negative. Let's see. Maybe 17. Let's see what is the exact value. Yeah, 17,778. Okay, so I did get 17,778 17.78 negative from some students. Yeah. Okay, that would be the corresponding values in C, in Celsius, in the Celsius scale for the degrees Fahrenheit. Now we want to find out what would be in Fahrenheit for 100 C, which is the point of boiling, with the temperature of boiling water. Here you go, we get 212. Okay, that's how we convert it. And then we have this other Kelvin scale that is even more important than any of those two. Okay, the Kelvin scale is the one that's adopted throughout by the scientific community as the main scale to measure temperature. So how do we do that? Okay, the temperature for Kelvin. Here you go. I'm gonna make a ruler here, right? Kelvin is one difference in degree Kelvin. We don't say degree Kelvin, by the way, right? We say Kelvin. Here you go, Kelvin. A difference in degree of 1 degree Kelvin is equal to 1 degree C. Okay, if here this one here is 273, and by the way, this is at 0 degrees C, we have 273 Kelvin. Okay, here would be 278 Kelvin. It's a much simpler relation because the distance, the difference between degrees Kelvin, the difference between 1 unit of Kelvin is equal to 1 unit of C. Okay, and the equation is, let me write it down. Okay, Kelvin scale. And that's the most important. You're going to understand why it is important very soon. Kelvin scale goes like that. Is 273 plus the temperature in C, in the Celsius scale. Okay? That's kind of straightforward. Now, why? Why do we define the Kelvin? Well, there is a reason for that. Okay? Why do we define the Kelvin scale? Well, the reason is that because there is an absolute 0 degrees, an absolute 0 temperature. There is. Scientists discovered that you cannot go below this the absolute 0. There's an absolute limit. Let me see. There's a absolute limit for the lowest temperature. Okay. This temperature we call the absolute 0. This temperature we call the absolute 0, which we give the name 0 Kelvin. There is no such a thing. There is no such a thing as -1 Kelvin. Doesn't happen in the universe. There is no such a thing. Okay? And there are experiments that shows that. Now, what else do we have to know? We talked about the temperature, right? Now we're going to talk about something else that's related to temperature. And the name of this quantity is called thermal energy. Okay? Thermal energy. There is heat and there is thermal energy. That is, which is different from heat. I'm going to tell you what the difference is. What is thermal energy? Okay. I'm going to make a drawing here for you. That's the next slide. Okay. So if you have a container right in here, and you are measuring the temperature of this container with my thermometer. Let me get my thermometer here. Here you go. I'm going to copy this thermometer and stick it here, and I'm going to make it smaller as well, otherwise it doesn't fit here. Okay. People do that. I have a machine like right in here. I have a machine that has a thermometer on that. Okay. You know, so let's say we have a gas, a warm gas. A very good way of modeling this gas is in terms, and by the way, it's not just gas, can be any substance. Every substance is made of molecules. Okay, here you go. I'm gonna denote those substances as points. Oops. Here you go. Like that. And a very good way of visualizing temperature is in terms of the velocity, the speed of those particles, of those molecules inside the container. Okay? Gases are made of molecules and atoms. Liquids are made of molecules and atoms, and so are solids. Okay? And the higher the temperature of those particles, well, the particles that make up the substance, the higher the temperature, the faster the particle travels. Okay? So here's the vector velocity of this particle. This particle here is traveling is lower than this one. So this specific particle has this temperature of this specific particle would be lower than this one. Okay? That's how you should visualize thermal energy. The thermal energy of this particle is higher than the thermal energy of this particle, and it has to do with the temperature. Okay, thermal energy is measured in joules. Here you go, different from heat. Thermal energy is the energy of a given substance. Okay? It relates closely to its temperature. The faster the molecules in a substance, the warmer the substance is. That's how you should visualize it. It's what we call the translational kinetic energy. So the thermal energy is related to the translational kinetic energy. Okay, so thermal energy is related to the translational kinetic energy of the gas. Okay, we call thermal energy when we are treating the gas in a macroscopic fashion. But if you look at a microscopic fashion, we call it translational kinetic energy of the gas, of the substance. Let's put substance. at the microscopic level, not fashion, but level. Here you go. There is both the microscopic level and the microscopic level. Did you picture that? That's the picture that you have to have about thermal energy. And it is dependent on the temperature of the substance, of the molecules that make up the substance. At absolute zero, there is no movement whatsoever of those molecules. There is no translational energy of those molecules whatsoever. 552. Okay, now let's talk about heat. Here you go. I have a slide about that. Let's see here. Yeah, I have this slide here. Physics, temperature, and heat are two different concepts. Okay, and there is also thermal energy. Thermal energy is different from temperature as well. And thermal energy is also different from heat. Let's talk about heat. Okay, the definition of heat is right in here. It's right in here. Okay, so you go, things goes like that, or goes like that, right? Temperature, you know, thermal energy. We have, here you go, we have energy. We have thermal energy. And you have heat. Okay, we have heat. What is heat? Okay, so thermal energy is just intrinsic to a substance. That's what it is. Thermal energy is energy intrinsic to a substance. What is heat? Okay, heat is transfer of energy. That's what heat is. If you're getting the heat, that's because the energy is being transferred to you. That's the difference that we have. So if you are warming up a substance, you are transferring energy to a substance. And this transfer energy is heat. As the substance becomes warmer and warmer, the molecules inside the substances start to travel faster. Okay? And you go ahead, calculate the kinetic energy of all those molecules in there, and you get your thermal energy. Okay? That's how we go about it. So when you warm a substance, there are several ways of doing that. You are transferring energy to the substance. This transfer of energy is called heat. Okay? Then you stop heating the substance. You know? Stop heating the substance. Stop transferring energy to the substance. What's gonna be left behind? You know, what do you have? You know, you have a bunch of molecules and atoms traveling faster than they were traveling before. Moving faster, traveling. Let's put moving faster than they were moving before. Okay. You calculate the overall kinetic energy of every atom and molecule in this substance, and you get what we call the thermal energy of the substance. Okay? That's how you should look at it. That's how you should look at the thermal energy. You can have thermal energy without having heat. Okay? But you cannot have heat without thermal energy unless you cool down the substance to 0 Kelvin. Okay? Here you go. That's important. You may have, let's say, here you go. You can have thermal energy without heat. Okay? But you can not have heat without thermal energy. Okay? If you're having heat, you are adding thermal energy to a substance. Thermal energy is 0. Thermal energy of a substance is 0. Of a substance is 0 at 0 Kelvin. So those are the ideas that you have to have in mind. 557. Any questions?
Yes, I have a question.
Yeah, go ahead.
So I know this is unrelated, but has our homework 2 been graded?
No, not yet. Not yet. I'll be doing that. I'll be grading it very soon. Well, today
okay.
I won't be able to grade it, but tomorrow definitely, yeah. I'll be able to grade it tomorrow. Okay? And anything else?
So is Kelvin the Fahrenheit plus 273?
No. Kelvin
Oh.
is the, here you go, Kelvin, let me write down the equation. I didn't wrote down, right? Oh, here you go. It's not Fahrenheit, it's Celsius.
So K equals 273 plus Celsius.
Plus Celsius, yeah. If you want
And
to.
then
Yeah.
So 1 degree of Fahrenheit equals how many degrees Celsius?
Half degree Celsius. Well, one difference. Oh, wait a minute. You gotta be careful, right? A difference in 1 degree Fahrenheit is approximately, let's see, is slightly less than half Celsius. A difference. Now, if you ask me how many degrees Celsius is 1 degree Fahrenheit, that's a different question, right?
Yes.
Which one are you asking? Are you asking 1 degree
I'm
Fahrenheit,
asking-
or are you asking 1 degree Fahrenheit of difference, a difference of 1 degree Fahrenheit, right?
Yeah, so how many degrees Celsius in 1 degree Fahrenheit?
In 1 degree Fahrenheit. Okay, so you gotta use that equation, right? Here you go. 1 degree Fahrenheit, you use this equation right here. Let me get here you go. I'm gonna write that down here. 1 degree Fahrenheit, right?
Mm-hmm.
And then we solve for Celsius, which is gonna be very close to 0 degrees Fahrenheit, right? Minus 150, see? 155 divided by 9. Here's 160 divided by 9. It's very close. So here you go. Calculate. Okay? Now,
So
yeah.
Oh.
Now,
So if
yeah.
oh,
Go ahead.
so F equals 1 minus 32 negative 31 times 5 over 9. And negative 31 times 5 over 9, that will be the amount for Celsius. Or negative 31, 95 times Celsius is equal to negative 31. That means then negative 31 divided by 9 over 5 or times 5 over 9.
Okay. Are you following here the how I did in the derivation? See? Fahrenheit equal to 1 degree. Is that's what you're talking about, right?
Yes.
Okay. Yeah. So that's what you get. Okay.
You got it. Thank you.
Okay. Any other questions? Okay, so there are laws of thermodynamics as well that you have to know. Okay, let's see how many. Yeah, there are 4 laws of thermodynamics. Here you go. There are 4 laws of thermodynamics. Okay. We call it the zero law. The first law, second, and third. Okay, so 4 laws of thermodynamics. Let's see, doesn't look like the book talks about the 0 law of thermodynamics. Yeah, unfortunately they don't. But it's kind of straightforward. Okay, the 0 laws of thermodynamics is so straightforward that it seems that there is nothing to it. Okay, so the 0 law of thermodynamics goes like that. 0 law goes like that. Okay, consider 3 objects. 3 objects, A, B, and C. Okay. So if A is in thermal equilibrium with B, okay, and I'm going to define what thermal equilibrium is, and B is in thermal equilibrium with C, what does it mean? This means that is independently, we call that is independently in thermal equilibrium with C. This means that A with B, B with C. This means that A is also in thermal equilibrium with C. Okay? Consider 3 objects. Here you go. If A is in thermal with B, 2, and B is independently in thermal equilibrium with C, then this means that A is also in thermal equilibrium with C separately. Okay? It's it seems so obvious that people didn't even bother about formulating this law, but it becomes very important in certain cases. Okay? So if you know that now what's thermal equilibrium? What's thermal equilibrium? Thermal equilibrium means there is no heat transfer between the substances. Okay? That's what it means. In other words, they are at the same temperature. That's what thermal equilibrium means. Okay? Graphically speaking, here you go. So here you go. I'm gonna have my 4 object. Is easier to understand when you make drawings, right? 4 objects, 3 objects. Here you go. Oops. A, B, and C. They don't have to have exactly the same size. You know, here's A. Oops. Here's A. Object A. Here's B. Here's C. Okay, so the way it goes is like that. If A and B are in thermal equilibrium, and how do we denote that? We denote like that. We put them in contact. Okay, not only put them in contact, but we put them in a styrofoam box. Okay, so there is no one else interacting with them. Here you go. This is my styrofoam box. Okay, like that. If A is in thermal equilibrium with B, and here you go, B is separately in thermal equilibrium with C, this implies, okay, this implies, I'll put like that, and this implies that A is in thermal equilibrium with C as well. Can you memorize that? That's easy, right? In a drawing format, it becomes easier to memorize that. Zero laws of thermodynamics. Law of thermodynamics. Like that. 6:10. Let's have a break now, and then we start talking about the other laws too. Okay? We have the first law, and by the way, this zero law came after the other three. Okay? When they realized that the zero law was important, the other three laws had already been formulated, and so they decide, okay, since this one is very important, much more important than the others, let's call this one the zero law. Okay, so 6:10 and break from 6:10 to 6:25 p.m. And don't forget the exam is going to be in 1 hour and 20 minutes. I see you in 15 minutes. Let's share the screen again. Go. And oh, by the way, let me set up something here. Hang in there. I need to set up. It's so strange. This computer program that records my screen keep on flashing in my eyes. I do not know why, and it's so distracting and annoying. I sent an email to the guys that sold that to me. I'm asking them how to how to make this thing stop flashing my eyes, you know. Okay, so here you go. Okay, so thermal energy has energy, you know. Thermal energy, here you go, has units of temperature. It has units of energy. Okay, heat also has units of joules of energy, but they're different. The square bracket here means unit, right? Here you go, equal to joules, equal to J. Now, let's go for the first law, okay? First law of thermodynamics. You gotta memorize those. Here you go. First law. This first law is easy. It's easy to understand. Okay? Okay, so how is the first law? They formulated. Okay. So here you go. When heat flows to or from a system, the system gains or loses an amount of heat equal to the amount of heat transferred. Okay, so that you know, this is conservation of energy. Okay, that's what it is. This statement is a conservation of energy. The sun transfers heat to the earth. The amount of heat that the sun transfers to the earth, well, not just to the earth, let me see, the sun transfers heat to the surrounding environment of the sun, okay? So the surrounding environment gains heat from the sun, the same, and the sun is losing that amount of heat that the surrounding environment gains, okay? Doesn't have to be only the earth, but because you have to integrate the whole heat lost by the sun around it. That's what you have to know. And that's the first law of thermodynamics. Let's see, when we, wait a minute. And now we also have an equation for that. Okay? This first law results in a mathematical equation, which is also very intuitive, okay? So here you go. Heat, the book says heat transferred. I prefer heat added. I prefer heat transferred because the heat can be negative too, okay? So here you go, internal increase in thermal energy plus external work done by the system. Man, this thing we usually put in a much smaller equation. Heat we usually represent by the letter Q, delta Q. Increase, if you are losing heat, delta Q is negative. If you are gaining heat, delta Q is positive. Okay, increasing energy, how do you denote that? We denote that by delta E. Okay, and external work done by the system, we denote by the letter W. by the system. Here you go. By the system. And don't forget to put a lower by, like that. Okay? Delta Q means Q final minus Q initial. Delta A means E final minus E initial. And by the way, we also call that internal energy. We usually call that internal energy. That's the thermal energy of the system. Okay? Okay, so let me give you an example. Okay? If a system absorbs, 100 joules. A system absorbs 100 joules of energy. Here you go. I'm going to make it easier. A solid object absorbs 100 joules of heat from the sun. Okay? What is the increase in thermal energy? Oh, from the sun. And it does not do any work in the process. Okay? That's an example. Here you go. Example. An object. I'm not even going to say an object. I'm going to put a solid object. I'm going to say an object absorbs 100 joules of heat from the sun and does not do any work in the process. What's the increase in thermal energy? What's the increase in thermal energy? Well, I'm talking about the increase in thermal energy. What is the increase or decrease in thermal energy, right? Straightforward, right? Can you do that easily? Okay, that's straightforward. Here you go. We have 100 joules of heat coming from the sun. That's adding heat to the system, to an object. The object does no work whatsoever in the process, which means the work done by the object is 0. So how much energy is increased? How much internal energy is gained by the system? 100 joules. Okay? That's the easiest problem that you can get out there. So the system gained 100 joules. That's one example. For the first law, let's talk about the second law. Okay, second law is kind of easy to understand, okay? Heat flows from a region that is warmer to a region that is colder. Okay, so heat flows from hot to cold. Heat flows from hot to cold. Okay? So the sun is much warmer than the earth, so the heat comes from the sun towards the earth. Example, right? The case of the sun. The case of the sun. It is warmer than the earth, and heat flows because of that Because of that, heat flows from the sun towards Earth, and not from Earth to the sun, and not from Earth to the sun. Okay. From an object that is a higher temperature, we go from hot to cold. From an object that is at a higher temperature to an object that is at a lower temperature. That's how heat flows. That's the second law of thermodynamics. And then we have the third law of thermodynamics. Those are all statements that we observe when we perform experiments, okay? We have never seen a case in which heat flows from cold to hot. And by the way, heat flows naturally, okay? That's very important. We gotta put here this naturally. You can have heat flowing from a cold object to a hot object. It's possible. Yes, it's possible. But then it's not a natural flow of heat. You need a machine to do that. Okay? An air conditioner unit is a machine like that. Okay? Note C, here, let's put it this way. Note C that this holds true only if there is no machine performing work, okay, to make the heat flow from cold to warm. Okay, it is possible to have the heat flow from cold to warm, but you need a machine to do that. Okay, here you go. It is possible. That's why I put naturally, right? It's possible to have heat flow from cold to hot. It is possible, but you need a machine to do that. You need a machine to do that. Like the case of air conditioner unit. Like the case of an air conditioner unit or a refrigerator. In a refrigerator, there is flow of heat from the refrigerator to the surrounding environment. Air conditioner too. Air conditioning extract heat from a room and dump outside. Outside may be warmer, but air conditioning can do that. But that's not natural flow. Okay? It's possible, yes, but this is not natural flow. Natural flow of heat. Okay? That's an important word here for the second law. The book used the word spontaneously. Okay? Naturally, spontaneously. / spontaneously. From hot to cold. And the third law is no system can reach absolute zero. Nobody has ever observed a system that is at 0 degrees Kelvin, 0 Kelvin, at absolute zero. Nobody has ever observed a situation in which heat flows spontaneously or naturally from cold to hot. Only if there is an intervention of a machine. Okay? Nobody has observed a case like that in which A is not in thermal equilibrium with C. Okay? Nobody has ever observed a case like that in which A is not in thermal equilibrium with C. Nobody. And the case of the first law, yeah? This relation always hold true. Okay, so here you go. Let me just write down what are the sections so far, sections of the book so far. 6.1, we're not going to be able to cover everything, okay? 6.2, 6.1 in my book is temperature, 6.2 is absolute zero, 6.3 is heat, and yeah, 6.4 is quantity of heat, and 6.5 is the laws of thermodynamics. We are not covering 6.6, we're not covering 6.7. Oh, we are going to cover 6.8 because this one is easy, and we're going to cover 6.9. So we can finish that. Okay, here goes 6.8 and 6.9. You have let me write that down for you in case those sections are different in your book, right? 6.1 is temperature, the concept of the idea of temperature. 6.2 is absolute zero. 6.3 heat. Oh boy, mistyping here. 6.4, the laws of thermodynamics. 6.5. Oh, wait a minute. Heat. 6.5 is quantity. 6.4 is quantity of heat. Quantity of heat. Okay. 6.5 is the laws of thermodynamics. 6.6, 6.7 we're not going to cover. It's too much. 6.8. It's thermal expansion. 6.9 is expansion of water. Water is a very odd substance, you know. I like to tell that to my students. Expansion of water. Here you go, put that between parentheses. Water is a very odd substance. It behaves in a very odd manner. Odd substance. It behaves in a very odd manner. Okay? That was all about thermal expansion, you know. You should know that, right? The warmer an object becomes, the larger it becomes. It becomes in general, but that's in general, okay? But that's, don't forget, it's in general, okay? In general. So that thermal expansion is all about. Here you go. You can take a look at your book. They have very nice examples in there. Okay. Let me get here into the internet. Here you go. Thermal expansion. Hopefully you can find some nice drawing, some nice. Here you go. Thermal expansion. Maybe Wikipedia has it. Okay. Here is what engineers do to prevent thermal expansion in roads. Okay, and let me see if they have. There's the classical case. Oh, railroad. Okay, here you go. Railroad tracks. Okay. At the time that people didn't know much about thermal expansion, they would make the mistake of building railways in a single long piece. Okay? Think about a very long bar of metal subjected that's fixed at the other end, at the other two ends. At very hot days, they would expand the lengths. And since you know, think about that, you know, I have my ruler here, right? And my ruler is fixed at those two ends. Suppose that suddenly my ruler start to expand because of thermal expansion. Okay? It's gonna bend like that. And you can even get damaged. Just like it happened to this railroad here. Here, here. And then you can damage the whole thing. You cannot drive your trains through there. Okay, that's how the importance of thermal expansion is all about. Let me see if we have a more dramatic case. Oh, glasses, they crack, right? Whenever you warm them too quickly. They crack, why? Because the glass expands very quickly and causes fracture in the structure, in the device. Okay. Let's see if we have another one. Yeah, okay. So let's write that down here. The book has an even nicer example of thermal expansion of the railroad. I don't see that here on Wikipedia. Okay, if you have the book there, you may have this picture in there. Okay. So in general, objects expand when their temperature increases. Here you go, thermal expansion. Thermal expansion. In general, objects expand when their temperature increases. Okay? But don't forget, it's in general. There are some oddballs out there. There are some oddballs, you know, but they're not the rule. They are the exception. There are some oddballs out there. You know, substances that contracts whenever their temperature increase. But these substances are the exception rather than rule. Okay, I'm gonna show you. Let me see if I can get one here for you to see. Those substances that contract with increase of temperature, they have some neat applications. Okay, and they even sell those things out there. It's not the regular way the substance behaves, but we do have them. Here you go. I have one here. Unfortunately, I don't have a heat gun here with me. If I had a heat gun, I could make a demonstration for you. Okay, they call it heat shrinking tubing. Okay, it's a tubing. They sell those heat shrinking tubings in different sizes, different diameters, and they're very reasonable. You can buy them. Those things are manufactured in mass. This one is a very large one, but I have a smaller. It's smaller than that. Let me see if I can find the smaller ones. Yeah, this. Oh, here you go. I got it. Here you go. Heat shrinking tubing. Remember, those materials are exceptional. Okay, they are exceptional. You don't find substances like out there that shrink with temperature. Most substances, they expand with temperature. Do you see here? I have a bunch of those. They sell those boxes out there at the electronics store. We use those things to insulate wires, copper wires. We put the copper wire inside this tubing, apply heat, and this polymer shrinks in size. Heat shrinking tubing. The polymer, the plastic that this material is made of, they have even a name for this plastic. Let's see here, polyolefin. That's the name of the plastic. polyolefin. Okay, here you go. I would love to make a demonstration of that for you. Let me see if I can find the. I believe I have my heat gun. Hang in there. Oh yeah, I found it. Here you go, the last box. My box of toys, right? Here you go. Hopefully it's here. Yep, right in here. Heat gun together with my computer and dusters. Has anybody played with those heat shrinking tubings? Anybody? If you play with electronics, if you play with circuits, you should be familiar with that. Let's see, I need to sacrifice one of those so you can see that happening. So that you can see this one shrinking. Once I apply heat to that, I don't use it anymore. I throw it away, right? Here you go. That's one of those heat shrinking tubings. Here's my heat gun. It's nothing but a fancy name for a hair dryer. Hair dryers are heat guns. I hope this thing still works. Long time I don't use it. Here you go. Electric heat tube, right? Mini heat gun. Here you go. Mini heat gun. I'm gonna turn it on. Okay. Here you go. I'm going to approach the heat gun to the tubing. Yeah, it's starting to shrink. See that? Shrinking, shrinking, shrinking. Okay. You can clearly see that this guy doesn't expand. This is an oddball. This is an oddball material. Most substances out there expand with the heat. And the coefficient of linear expansion of this guy here is very high, relatively high. Okay? And we have some application for that, like I said. Contracts and shrinks permanently. It doesn't revert. Doesn't reverse the size. Okay? Here you go. Here in the book you have an example too of a brass strip that can be used as a thermometer. Take a look there, okay? Now, in order to counter the effects of heat expansion that can damage a railroad tracks, not just the railroad tracks, but also the bridges, you know, what people do, they put expansion joints here. Take a look. We have this concrete bridge that may expand and crack, right? If you don't put this joint right in here. Look, we have a gap here in this joint. See that? So we have pieces of concrete, slabs of concrete that are placed in the bridge, and you have a little gap between them to ensure that those concrete is not going to become damaged when they expand or contract. So that's how engineers, that's the solution that engineers found out to ensure the safety of the bridge, to ensure that the bridge is not damaged from thermal expansion. And the same thing, something similar can be done to railroad tracks to prevent that bending. We call it buckling. Okay, what you see here is called buckling. Buckling, okay, rail buckling. Thermal expansion of long continuous sections of rail tracks. If the rail track is very long, then a very small expansion is going to cause something like that. Okay? And then we can get to the water. So here we go. Let's go. Thermal expansion. In general, objects expand when their temperature increases. There are some oddballs, however. However, there are some oddballs there. Substances that contract whenever their temperature increases, like heat shrinking tubing. However, the substances are the exception rather than the rule. Okay? Thermal expansion is a problem in large structures. For instance, long rail tracks can buckle and become damaged. For instance, long rail tracks and bridge decks can buckle and become damaged if they're not deployed properly. Okay? In both cases, you can solve this problem by applying what? Here you go. Go back to the Wikipedia here. By using expansion joints. Which have a gap to ensure that the structure does not buckle. Okay? Does not buckle. That's a practical application of this idea of thermal expansion. And now we're going to talk about expansion of water. 7 o'clock, we have half an hour before the exam, right? Any questions? Okay, remember what I told you? Water is a oddball substance.
Oh, yeah, I just have one question.
Yeah?
Yeah, I know since exam 2 is not graded yet, is the 3A or 3B graded or no?
Let me see.
Oh,
well, let me see.
Sorry, no. Never mind. Sorry, because it's due tonight. Never mind.
Yeah, it's due tonight. Homework 3A, 3B is due tonight. Yeah, that's right.
Yeah, I forgot it's due tonight.
Yeah. So here you go. Water is an oddball substance. And what do I mean by oddball substance? Okay, I mean that at a small range of temperature, water contracts let's see, let's put it this way. Water expands when the temperature increases, okay? But only within a certain range of temperatures, when the temperature increases. But only within a small range of temperatures. Okay, so, and that's important. This is a very important thing. We are around here because of this oddball behavior of water. What's this? How does it work? Okay, over most ranges of temperature, water expands. But there is this small range of temperature between 0 degrees C and 4 degrees C that water, contracts when the temperature increases. Or let's say water expands when the temperature decreases. Here you go. I make a little mistake here. This temperature range is between 0 and 4 degrees C. Okay? So let me show you. There is a very nice drawing in your book. Let me see if I can find that in the internet. Okay. Well, thermal expansion of water. Right? Let's see if we can find. No, I don't want academic articles. So let's see if I can get an image, a nice image here. Yeah. Let's see. Here you go. I like this one. Okay. So here what happens? That's the volume of water in cubic centimeters. As the temperature increases, the volume of the water increases. But between this range of temperature, between 0 and 4, it happens all the way around. Okay? At 4 degrees, when you decrease the temperature, water starts to expand between 4 and 0. Okay? Here, the density of the water is, from here to here, the density of the water is decreasing. No, sorry, it's increasing, the density. The volume is decreasing, but the density is increasing. Okay, and from 4 degrees to other temperatures, the density decreases because the water is expanding. The same amount of mass is becoming larger. Okay. Here you go, another nice illustration. Okay, at 70 degrees, the water, between 70 and 140 degrees, water expands. And if you're not careful, water the volume can become so large that it can overflow. Well, it's not water, it's another liquid here, because water at this point should be boiling, right? Let's see. They don't say what material is. Okay? Did you get the idea? That's the oddball behavior of water. Here you go. The oddball behavior of water. It's because of that ice floats in water. Solids objects are usually denser than their liquid counterpart. Solid objects, So if you have a container of liquid iron, right? It has to be very hot. And you get a block of iron and drop it in this container of liquid iron, the block of iron is gonna sink because it has a larger density. But that's not the case of water. If the ice is between 0 and 4 degrees, if the ice is at 0 degrees, it's gonna float in liquid water. So let's write that down here. And that's very important because for evolutionary reasons. Why is that? If suppose that the lake, our lakes, suppose that water in the lake wouldn't behave this way. During the winter, a pool of water would become frozen from the bottom up to the point that the whole volume of water would be a complete solid, and no fish would be able to survive something like that. Fish wouldn't be able to swim in ice, right? Fish can always swim in water. So, because at 0 degrees C, ice water has a lower density, it ends up floating on the liquid. And you form a thin layer of ice and you still have liquid downwards. That thin layer of ice acts as a thermal insulator for the rest of the lake. I can write that down here for you. It's a very nice phenomenon, okay? Think about that. So from the viewpoint of evolution, maybe we wouldn't be around here if it weren't for this property of water. Water expansion, okay? Its temperature range is between 0 and 4 degrees, okay? So between 0 and 4 degrees. I already wrote that down. I'm not gonna write that again. Okay. This behavior has very important consequences from the evolutionary viewpoint. Okay, why is that? Okay, think about a body of water, such as a lake. Because of this oddball behavior of water, water between 0 and 4 degrees C tend to have a lower density than warmer water. This colder water tends to float. If temperature goes down further, only the top layer of the water will freeze. Okay? Because the water at the top is less dense than the water of the bottom. Will freeze. Okay? This also causes the ice at the top to thermally insulate the remaining liquid, preventing the whole volume of water to become frozen, which would not be good for fish, right? Fish wouldn't be able to swim around. So let me get here. I'm gonna copy this image and paste in my notes the oddball behavior of water right in here. Okay. and 4 degrees C. Here you go. And that's what we have for this chapter. It's 7:15 right now. You know, why don't we have a break, right? Let's have a break. Let's have a 15-minute break before the exam, so you can get ready for what's coming next. And I will adjust here. Here you go, thermal energy. Yeah, thermal energy. Heat transfer is the next one. Is the next topic. Heat transfer is an interesting material. Okay, heat transfer. So most likely we will have to do electricity and magnetism in the other. Maybe we'll be able to start electricity next time. Let's see how it goes. Okay, that's 7 and 8. That's gravity. Let's see here. Yeah, that gravity is what? 4, 6, 4 and 5, right? Projectile motion. Let's see. Yeah, it's 5 and 6. Here you go. Now, wait a minute. Gravity. Let's go to the. Gravity is 4. Yeah, okay, so this one is not right. This one is not right. Here, gravity is 4. And fluid mechanics is 5. Here you go. Thermal energy is 6 and 7. Heat transfer. Thermal energy is 6. Okay. Heat transfer is 7. And if we manage to do electricity, next time we will cover 8. Okay, that's homework 4 and 5. And that's going to be 9. Maybe it's going to be 8 and 9. Electricity and magnetism, maybe. Electricity and magnetism. We won't be able to cover that yet, right? So waves and sound. Now, heat transfer today is the 20. That's good. So that's where we are right now. Thermal energy and thermodynamics 6. Heat transfer is going to be 7. Okay, so 7:15 right now. Let me save this guy here and I'll see you in 15 minutes when the exam starts.
When will the PDF for exam 2 be posted?
PDF for the exam 2? You want to know when I'm going to correct the exam 2, right?
No. When is the PDF, the questions for exam 2?
Are you asking exam 2 or homework 2? What are you talking about?
I'm asking when is the exam 2 going to be posted for
He's
the
gonna
PDF?
post it at 7:30.
I'm gonna post at 7:30. The questions,
Oh,
okay.
okay.
I'm gonna post at 7:30. So hang in there. Let's see, Rhonda is trying to come in, right? So